one another. So we've talked now about orthogonal frequency division multiplexing, and I'd like to move on to the next topic, which is discrete multitone, which is another type of OFDM. In fact, it's kind of like an optimization of OFDM. So there's a little ambiguity in the naming of different strategies. So I'm going to use the vocabulary that when I talk about OFDM, I'm assuming that there is the same power allocated for each subcarrier and that I'm using the same constellation for each subcarrier. So if I'm using QPSK on one subcarrier, I'm using it for all of them. So that's what I call OFDM. Now I'm going to move on and discuss something called discrete multitone, or DMT. And in this case, we're going to optimize both the power and the modulation choice for each subcarrier. So we're going to violate these assumptions. And we're going to do this in order to maximize the channel capacity. So it's like an optimization of OFDM. So in OFDM modulation, we know that we're transmitting with equal energy, so all the same height, and with the same modulation format. So here I'm showing QPSK. But we know because of channel impairments, we're going to receive a spectrum that looks different from the spectrum which is transmitted. For instance, there could be a deep fade on this sort of third subcarrier in this illustration. So given that I know that the channel is going to make things uneven at the receiver, why should I keep everything even at the transmitter? In fact, what I want to try and do now is not just be robust to the impairments of the channel. Remember, the strategy of going with OFDM was to avoid equalization, because in each one of the parallel ones I didn't really need equalization because their multipath effect was counteracted. But maybe I could go farther. Maybe it's not just a question of avoiding equalization, avoiding intersymbol interference. Maybe I can actually do another kind of level of equalization, if you will, by taking into account what's going on in the channel. So let's think first in one direction. Suppose that I'm interested in optimizing the choice of modulation. Well, for instance, since I know that the third subcarrier is going to be the most impacted, maybe that one I will use the most robust modulation format. So I'm going to use BPSK on that one. Now I look at the fourth one, and the fourth one has a really high peak. You know, it's going to keep its signal-to-noise ratio unaffected by the transmission. So on that one, I'm going to use my most aggressive modulation format. Let's say 16 QAM. Now, the first one is stronger than the second one, so maybe I'll use 8 QAM here, and I'll use QPSK here. So the idea is that when I get to the receiver, the signal-to-noise ratio at the receiver is going to be worse for some subcarriers than others. But, of course, each one of these modulation formats has a different probability of error. And now I will have different SNRs, but I'll have different probability of error curves, and I'm going to try and pick them so that, you know, I get pretty much the same performance on all my subcarriers when I get the reception. So there's another DMT strategy we could use. Suppose that we didn't change the modulation format. We left it all QPSK. And then we instead started to play with the allocation of power on a subcarrier basis. So we could, knowing that the third subcarrier is going to be heavily attenuated, we can boost its power so that when it arrives, it has a decent EB over N0. And so we could, given a specific power budget, do an unequal division of that total power across our subcarriers. So this would be another way that we could try to optimize OFDM by doing some per subcarrier optimization. For instance, we could have all of the received signal-to-noise ratios be equal, and therefore we could have QPSK, or the same modulation format for all of them that would lead to the same BER. So the important thing is same BER would be achieved because of this choice. So we've seen how, you know, sort of very straightforwardly, we could change modulation, or we could change the power allocation. But actually, suppose that we play with both of them at the same time. And if we play with both of them at the same time, we can actually maximize our channel capacity. In fact, there's two kinds of optimizations that we can do, and it depends on whether we're trying to optimize the probability of error or if we're trying to optimize the total throughput in our channel. So both of them could be valid targets of optimization. So these are the two choices we'll be discussing. First of all, this approach they're for linear channels. We assume that the only impairments they encounter is this frequency response for the channel, which makes it unequal per subcarrier. So it's not flat, but it is a linear channel. It is fully described by the frequency response of the channel. So let's look at our first optimization choice. Suppose that it is the performance, the quality of service, or the probability of error that we would really want to be very certain to achieve. And this would be important if we're operating at the near the threshold for forward error correction. For instance, there would be a scenario where it would be critical to fix the probability of error. And suppose that subject to that, we have to respect this probability of error. Well, what would be the maximum data rate that we could transmit for a given channel? So what allocation of bits, modulation format per carrier, what allocation of power per carrier would achieve this probability of error and at the same time maximize the total data rate that was being pushed through? The other way I could do my optimization is to start with a data rate which is fixed and find the probability of to minimize the probability of error when I reach that RB. So again, just depends on which one is our main target, but we'll see that the way of achieving these two different optimization goals is not dissimilar. So let's look now at the first choice. Suppose we have a fixed probability of error target, and we'd like to maximize the throughput, maximize the bit rate, the effective bit rate across all of the subcarriers for this transmission. So we're looking for a strategy. So how we're going to come up with a strategy of how to allocate bits or modulation formats and power per carrier. The first thing we're going to assume is that the subcarrier spacing is fairly narrow, so that they are fairly narrow, each one of them, so that we can approximate that the channel response is constant in each one of these subcarriers. So we don't have to have a curve describing the frequency response in the subcarrier, but there's one value, h of j, which represents the frequency response, the value during one subcarrier. And at the receiver, we can imagine that each channel, first of all, its noise is, whichever power was transmitted is going to be affected by h of j. Now, the noise should be the same for all carriers, right? Because the noise is flat across the frequency band, and it's typically thermal noise from the electronics, which is being added at the receiver. So now let's say that we have n sub I, which represents the number of bits in the bits per symbol in the constellation for subcarrier I. So for subcarrier I assign NI bits. If it's QPSK, then I assign 2 bits per symbol, a total of 4 constellation points for QPSK. If I use 16 QAM, of course, there's 4 bits per symbol, etc. So NI represents the number of bits per symbol. So the total transmission rate, RB, will be equal to the sum of NI times the frequency, the bandwidth of that channel. And of course, in most allocations, we're going to assume that there's equal subdivisions. Each subcarrier has the same bandwidth. And of course, this is assuming that we use the most spectrally efficient version just to be able to do our calculation. Now, the total power, P, is going to be constrained. So we have some power budget, this maximum power that we can transmit. But we're going to allocate each of the subcarriers with its own allocation of power, but of course we have to make the sum of this equal to P. So our goal in this construction is to find the allocation that maximizes RB, and it meets our error target, because in this one we're fixing the target. And there are algorithms which lets you go through and find for each Ni what would be the appropriate PJ. Now, how do these algorithms work? What is the concept behind them? In essence, what we're doing is we're seeking an equal probability of error for all subcarriers, because the total error probability is going to be dominated by whichever one has the worst probability of error. So if we keep them all the same, that's going to give us our best probability of error. So we're looking for a solution that gives equal probability of error across all of them. So how are we going to achieve that? Well, we know that the channel frequency response is not flat. So here is this curve where we can see the some arbitrary frequency response. That means since the noise is coming in and it's, like I said, flat across all frequencies, that means that if I look at any particular subcarrier, I would expect the signal-to-noise ratio will vary, because the noise is fixed, but the signal power will vary. So the signal-to-noise ratio varies across subcarriers. So I'm going to try and combat that happening. So just to give you a feel for how these algorithms work on this optimization, suppose I take this frequency response and I flip it over. I flip it over, so I go from, up and then down. I flip it over, and now it goes up and then down like that. And so this is sort of the inverse. And I think of this as being like a bowl. I think of it as the bowl with the bottom of the bowl is irregularly shaped. Now, since I've flipped it over, and I'm interested in the signal-to-noise ratio, because I flipped it over, what I'm interested in is the noise to frequency, noise to signal ratio. So how am I going to make it so that this ratio is the same for all of the subcarriers? So I can think of it as taking all of the power which I have available to me, thinking of it as being in a pitcher, and I'm going to pour it into this bowl which has an irregular base to it. Now, I keep pouring until it's empty. I've used up all my power. And now I can naturally see that there are different allocations in each one of the frequency bits. And, intuitively, I can see that I have done an allocation now which is going to keep the the noise to signal ratio the same for all of these channels if I use this power allocation. So naturally I would have this level. Now this is in giving less power to this channel, in the end the signal to noise ratio, or the noise to signal ratio, will be flat, because I pour it in, and for sure after I pour it in it's going to be a flat surface. That's how water works. So that's why we call it water filling. So now I know, if I look across each one of the bins, now I know how much of the water, how much of the power should go in each one of the bins. And that is why we call the DMT optimization solution a water filling approach. So we're basically equalizing the bit error rate performance by equalizing the signal to noise ratio in our power allocation. Note that in some cases I could pour in the water and I could run out of water. Suppose that the total power I had a level afterwards that we just poured in that much. That means that some of these frequencies which have a whole lot of attenuation will not necessarily be used. So that tells me right away that I am better off taking those bad subcarriers with deep fades in them, just not using them, just throwing them out, so that instead I can concentrate on the successful ones. So the successful one is here, and the deep one, I guess I'll try and go down here. That would be the deep one, and there it's going to get very good performance. So I'm going to, really invest there. But in the other one, if I didn't have enough power, I know that no matter how much power I put in, it's not going to be very good. So I'm better off abandoning it. So this is the water filling solution. Choice 2 is similar. It's just how we set up the problem. So now the data rate is fixed, and I'm trying to minimize the probability error, but still be sure that I reach that RB. So in this case, it's the total rate which is fixed. And again, I'm going to do a power allocation, but this time the power allocation is meeting that RB and minimizing the error. So in both cases, I'm trying to minimize, in both cases, I'm trying to come up with something that either makes RB best or makes the error best. But one of them, I always put a constraint on so that I cannot push too far in one region. Because, of course, if I let the bit rate go very low, in that case, you know, the error will be very low because I can use like BPSK and there's very few errors. But, of course, my throughput is going to be lousy. So I'm always going to have to protect one and push the other. And that is why there's two. It's just which one I'm going to protect, which one I'm going to push. So, in essence, what happens when we use DMT, whether we're using choice 1 or choice 2, how does it come out? Well, we say that in the end, what we have accomplished is an allocation of bits and an allocation of power on a per subcarrier basis. So here are all my subcarriers. Here is my frequency response, and over here would be a typical bit and power allocation. So where the frequency response is good, yes, we have orange there. And this section of the frequency response, everything's going well. That corresponds to the orange over here. And that's a place where I'm going to use large constellations because there's not much attenuation. So I'm going to see a large bit allocation there. And if I look at the ones with the deep fades, when I see deep fades, I'm going to have fewer bits allocated to those. So I'm playing, if you will, with both the power allocation and also with the modulation format to really try to get out the most that I can from both of them. You'll notice that in some cases, for instance here, actually that works out well, we have a severe dip, and that would be a place where I probably wouldn't put any bits at all. So let's look here at the bit allocation as a graph. And in the bit allocation, we can see that in the region where there's very little attenuation, we have the most bits per symbol. And when we get down to this dip, we're way down here, and we're actually going to be in 0. So I'm not allocating any bits to this. So in this case, I'm not doing any transmission. I'm throwing away those subcarriers because I see the deep fade, and it's not going to do any good. And then, of course, the other one is we have this numerical technique, achieving the water filling, doing the optimization, which tells us at which point we should move from, you know, BPSK to QPSK, etc., until we maximize the throughput for this channel. So the DMT approach, to contrast it with the OFDM, which is in the 802.11 standard, for instance, is that we will have different allocations on each one of these different subcarriers, different bit allocations, and different power allocations. So, in summary again, OFDM, equal power, equal number of bits. It's adapted to each channel. So, if I have a highly variable channel, DMT is not going to work because I can't change it that fast. So the idea of optimizing DMT is great, using DMT to optimize OFDM, but think about the 802.11 standard. Why didn't we go with DMT, where I could optimize things? I went with OFDM because I know that Wi-Fi is used in an area where people are moving. And in moving in the area, so I could be sitting at my laptop, I'm not moving, but people are moving around me, blocking the antenna, blocking line of sight. Quality of the signal can change very quickly. And so I want to have something robust to that, and that works in all of the circumstances. And that's why I took OFDM. Now DMT has to be adapted to the channel, so that channel cannot be too variable. So where do we see DMT being used? Well, historically, DMT was used in digital subscriber line So this is where we took a twisted pair installed in homes, which were installed in order to have voice communications on their telephone. But with the years, we were more interested in data communications, and since the cable was already there, we tried to exploit it. And that, twisted pair was already there, we tried to exploit it. And that twisted pair did not have a very good passband. It wasn't that big, and we were trying to push through a whole lot of data through a channel which was dicey. But it was a channel that was dicey, but a channel that was stable, does not change much. So that means that when you would turn on your modem at your home that would communicate with your telephone provider, who would also give you data service, it would check out that line, characterize it, get to know the frequency response, and then, okay, I can optimize this. And then it would use DMT. And it became very, very competitive. You could get very good throughput because you've done this optimization. But it only worked because it was a stable channel. So OFDM and DMT, different approaches for different situations. But essentially, the hardware, the techniques that I described for OFDM are also being used for DMT. It's just we do this optimization on top of that other hardware for the implementation of the OFDM.